So yeah, so first of all, the recording should be up. I realized this morning I never put the other ones on public. So I know if you're like subscribed, for example, like I put those out there and it pings you like when the videos come out. Um, so just know that they were viewable already, but now they're definitely viewable. But anyway, we're going to kind of continue our discussion on like statistics or sampling. Last time we talked about sampling, and then we went into central limit theorem, like why that's important. And then the plan was to kind of go into confidence intervals, but I wasn't sure if we were even going to reach that, which of course, we didn't get into it. That's perfectly fine because that's what we'll talk about today. Okay. And then I think there was some questions. Oh, you guys can't see my screen right now, can you? So let me go pull that up. I'm going to pull up the Google Doc right now. So I see some people put questions in there, which is awesome. Sorry, I'm just making sure I share the right screen. There we go. I expand this out. Okay. So I've left one of the questions in there just because it was referring from yesterday, this degrees of freedom, if you guys remember that, the DDOF. I looked it up and like, what is this D in front of the degrees of freedom? If you look up the documentation, it's delta degrees of freedom. And basically it's that weird thing, like I said, like it's divided by the square root of n-1, right? The DDOF, meaning delta degrees of freedom, you can adjust that. So instead of -1, you can have -2 or -5 or -10. So in this case, by setting it equal to 1, you're saying that standard deviation, calculate the standard deviation, but use degrees of freedom of 1. So that way you get the standard error versus like the standard deviation. And there's other reasons why you might have different parts, but it comes down to degrees of freedom. We should talk about this in the future because I think it is something that's kind of weird. And it'll actually relate a lot to t-distributions, which we'll talk about, should be talking about today, right? But anyway, there was a question that's new related to the above question. When should we pick NP stand X versus NP stand X DDOF? Basically, is that if you are using a sample, if you're doing the standard error. So do you guys remember the difference between standard error and standard deviation? Give me a thumbs up if you're like, yes. Give me a sideways, like, I know there's a difference, but I don't know what it is. Okay, I see a couple of thumbs up, see some sideways. All right, so the main difference is that your standard deviation is basically just saying the spread, right? We talked about how the distribution is spread out, like the sample, right? That's true for everything. When we have a sample, we like to be very specific in statistics and be like, hey, it's not technically the standard deviation of the population, it's the standard deviation of the sample. So when we say like sample mean, for example, we know, oh, that's the mean of the sample. So instead of statistics saying, oh, the sample standard deviation, there's a few reasons why they might do this, but basically we say, well, let's just call it something different called the standard error. And the standard error is therefore that part. When you do the standard error, you have to consider that n-1 part. And part of the reasons why is because, like, I'm not going to try to go into degrees of freedom because it can be kind of confusing, but basically it's the fact that we're using a sample instead of the full population. So we're kind of like losing a degree of freedom from our normal part. This is like me kind of hand waving these words, but basically like because we're taking a sample, we have to consider that. So does that answer? Give me a thumbs up if that made sense, like why you would use DDOF then versus like not. Sound pretty good? Okay. Short answer basically is like because we're using on a sample. All right. Discuss about error bar. So error bar, that's an interesting one because there's a whole bunch of ways we can do error. We're actually going to talk a little bit about like confidence intervals, and confidence intervals can actually also apply to error bars. Do you guys, give me a thumbs up if you guys know, like heard that term error bar before, or like know what I'm talking about when I say error bar. Give me a thumbs down if you haven't heard about that or don't really know much about it. Okay, so I see Christine Alvaro, thank you. And it's perfectly fine. Like that's why we all come from different backgrounds. So it's really useful to like for us to all talk about it so we're on the same page. An error bar usually refers to like if you have something, I'm just gonna draw like scatter plot points. So let's say you have like, you know, your X and Y axis and you have a scatter plot point here, scatter plot point right here. And I'm gonna draw this in a different color. Usually it's like in black or something, but just to make it really obvious, let's do orange. So usually you might have an error bar like this, like, and I'm drawing it really badly. So have you guys seen like plots like this where you have like a scatter plot point and then there's like little bars? And then if those people who are like, don't know what it is, they're like, that's weird. Like, why do you do this? This basically is trying to represent saying, well, we measured the point at that blue point right now, but we might have got, you know, that might just be the fact that we got a weird result, or, you know, if you're a scientific like if you're doing science kind of stuff, It might be like, well, our instruments might be slightly off, this might be the kind of error. So usually we call these like error bars or margin of error. Well, not margin of error. Well, it is margin of error. Basically, it's like how far off do we think this could possibly be? Yeah, keep it.
Are they also called residuals?
Yeah, you can also talk about it residuals, though that can be confusing too, because sometimes residuals can mean something different. Residuals can also be the difference from the data point to your predicted value. So for example, I could have something like a predicted model like this, and then saying how far away are you from here to here, that could be the residual. And so it depends what you're talking about. But in general, you can think of those little error bars as being like how much you think it could possibly be off. Okay, does that make sense to people? Cool. And this relates really closely to the confidence interval, which we'll get into. That's one of the first topics we'll talk about today. So it's always useful to know like who you're talking to, like who's showing this visualization, because different fields will display error bars differently. So it's always important to know exactly what it is. Usually, and this is not always, but usually that means within one standard deviation of what they expect of that. So this could be like a 65%, or not 65%, 68% confidence interval. But it all depends on the field too. And sometimes in science, you actually say, well, I know how accurate my machine is. I know how accurate measuring this thing is, and they combine it together to become the error bars. You might also see error bars on like bar charts. So like sometimes that's a horrible bar, but not that way. You might have a bar chart like this, and they'll have like a little error bar like this. This is just basically saying the same thing as if you imagine this bar chart as being a single point. Okay. Cool. Any questions on that or follow-up? Awesome. Cool. It's good to see these things because basically everyone uses statistics, especially like in the sciences. And us being in data science, we're going to see a lot of data, right? And so it's used to know how people are talking about it. So this next part, H0 and HA, representing null hypothesis and alternative hypothesis. We should get into this today with hypothesis testing. Has anyone reached this point? I think it's section 14 with hypothesis testing. Give me a thumbs up if you guys have started that. Okay, I see some head shakes. So that's okay. We're going to talk about that today, but I see some thumbs up too. So also you might remember a little bit of this if you did some statistics in college or in high school or something, but we'll get to that today. So I'm going to hold off of that. Two sample t-tests. Oh, I'll definitely hold off to this one because this definitely has a lot of information on it. But when calling stats.t.pdf to get the PDF on the t-distribution, degrees of freedom is the sum of the size of the blah, blah, blah. Sorry, just reading through. Can you explain why the degrees of freedom? Yes, we will come back to that because that is a whole good discussion that is really important. But we want to show what the t-distribution and t-test is first. Okay, cool. Any other questions that maybe like weren't on here, but you might have like immediately just based on what we've learned so far? Pretty good. Cool.
Like margin of error and how that like fits into like standard error and.
Yes. Yeah, margin of error is actually really simple. It can be kind of confusing because there's so many different terms. Standard error, remember, is kind of like the standard deviation of the sample. Margin of error is converting that standard error into a value versus like saying, oh, it's 1.3 standard deviations away. Or like, if you say z-score, it's a z-score of 1.3. You can say, well, 1.3, what does that mean? Oh, like our standard deviation was, let's say 100, right? Whatever that value is. You basically are just converting number of standard deviations. So let's say I have 1.3 standard deviations away, like a z-score of 1.3, and my standard deviation was 100. My margin of error is 1.3 times 100. So I would be 130, whatever value, flim-flams, pounds, whatever it is away. So that's what margin of error. It's just another way to state the standard error, but in something that's a little more concrete. Does that make sense?
Okay, thank you.